everyone. Welcome to the lecture series of VLSI Technology subject with the subject code KEC 053. This is the third lecture, and in the previous lecture we have got to know about the integration of IC technology, that what is IC technology, what is the basic structure of silicon crystal, what are the common defects and dislocations which are possible to occur during the crystal growth, and what is the starting material, that is a single crystalline wafer which is used in the IC fabrication technology, and how in the last lecture we came to know about the growth process which is used with the help of CZ method, Czochralski method, in which we grow a silicon ingot, which in today's lecture we will get to know about the next processing steps which are used in the silicon crystal ingot. So, in the last lecture we came to know about the segregation coefficient, which is the coefficient which is present in the silicon ingot because of the impurities, and we in the table we have seen in the last lecture that the segregation coefficient for all the impurities is less than 1, but for oxygen it is greater than 1, and this oxygen from where this oxygen comes in the silicon wafer? It comes from the furnace itself, it may come from the quartz crucible, and in the process we also use some water coolants so that the silicon ingot which is grown during the process, it can be cooled simultaneously. So, because of all three possibilities, we have oxygen in the silicon ingot. So, there is a possibility of oxygen incorporation during the crystal growth process, and usually with the help of this CZ grown crystal, the amount of oxygen varies from 5 into 10 raised to the power 7 to 10 raised to the power 18 per centimeter cube, and this oxygen will in the silicon will have three possible effects. First of all, this oxygen, 95% of the oxygen molecules, they will settle in the interstitial sites, right? Interstitial sites means suppose we have this silicon atoms, and in the remaining space, in the empty space, we have some O2 molecules. Okay, so this is the interstitial site and this is the interstitial molecule. So, 95% are the chances that these oxygen molecules will settle in these interstitial sites, that is they will find the space between the regular array of silicon atom and they will go there and sit and settle themselves in these spaces, and rest 5%, however, it can form a complex structure like SiO4 monosilicate, and that complex will act as a donor. So, and these donors are electronically active throughout the process. Therefore, it will affect the resistivity of the grown. They will affect the resistivity of the grown silicon, and the formation temperature for these complex is around 450 degree to 500 degree C. So, when the crystal is being cooled, this SiO4 complex will be formed and they will make a silicon N-type donor or another complex. So, what could be the solution to this problem? One solution is when we cut when we cut this silicon ingot into the slices, into the wafers, heat those wafers above 600 degree C. Okay, so when you heat that wafer above 600 degree C, those complexes will be dissolved because their formation temperature is less than 600 degree C, that is 450 to 500 degree C. And second thing is they have a very small thermal mass, so they will cool down very quickly and oxygen will not be precipitate easily. So, 95%, secondly, 95% of the oxygen that was incorporated in the interstitial site, so that oxygen in interstitial site will be actually beneficial to the wafer. Okay, so it will lead to some advantages in the silicon structure. it will increase the mechanical properties of the silicon, it will improve the yield strength. So, okay, so it is true that this information is true only when we have a very less amount of oxygen that is incorporated during the crystal growth, and that concentration should be less than 6.4 into 10 raised to the power 17 and per centimeter cube. So, if the oxygen concentration in silicon is greater than 6.4 into 10 raised to the power 17 per centimeter cube, the third problem may comes in picture, that is the oxygen precipitation. We know that the solubility of any solution will be reduced if you decrease the temperature. So, when the crystal is being cooled down, and if the concentration is greater than 6.4 into 10 raised to the power 17 per centimeter cube, it is going to precipitate in the silicon, and once it precipitates, it gives rise to the compressive strain, and that will stress the crystal, and it will start some dislocations from the side. So, precipitation forms is highly undesirable. Okay. So, although this precipitation is always undesirable because it will give rise to the dislocation in the silicon crystal. So, we can use it in our favor. How we can use it in our favor? Because we know that these dislocations can be used as a sink to the metallic impurities. They collect all the metallic impurities, and these are also known as gettering centers or gettering. But one thing should be kept in mind, that these gettering centers or sinks should not be on the top of the wafer, where we have to fabricate our active devices like BJTs or MOSFET. Okay, so those sinks should not be in the active area. Next is gettering. The gettering is done so that the active region of the device is free from the metallic contamination, and most of the device is actually contained in the top few microns of the silicon wafer. Suppose we have this silicon wafer, it is actually a disc shaped structure. The total wafer size is, suppose it is 300 to 500 micron. Okay, and the actual wafer fabrication is done only in this area from 5 to 10 micron. Okay, so the active device is fabricated only in this 5 to 10 micron area from the overall area of the wafer. So, this junction should be, this 5 to 10 micron area should be free from the contamination, and this is done with the help of gettering. There are two types of gettering. One is extrinsic gettering and the another one is intrinsic gettering. In case of extrinsic gettering, the back side of the wafer, which is not polished, which is not the polished side of the wafer, is subjected to pass through the electron irradiations. What will happen when we pass the radiations or laser light to the back side of the wafer? We intentionally, suppose this is the wafer, and at the back side of the wafer we pass some laser light. Okay, some radiations will be passed, means we intentionally create the sink to collect the metallic contamination. So, when the wafer is subjected to processing, when we make some devices on this wafer, if there are some metallic contamination, they will travel through the active region. This is the active region above side. The metallic contamination will travel through the active region, and the sink will be used to absorb all this metallic contamination, and your active region will be the area of the active region will be free from such contaminations. Next is intrinsic gettering. It is used, it uses the oxygen that is already present in the crystal. We know that oxygen above certain range, it will lead to precipitation, and these precipitations are usually undesirable because they will form the dislocation. Okay, so we can use it in our advantage, because it will provide, but make sure that they don't precipitate in the active region. So what we'll do in the previous slide, we have also seen that heat the wafer above certain temperature, above 1000 degrees C, in an inert ambient environment, and the oxygen from the near surface, it will be evaporated, and the active region will be free from the oxygen, and there will be no precipitation in the active region. But still we have the oxygen which is deep into the bulk, Suppose this is the silicon wafer. So oxygen will be there in the deep bulk, and from here when we heat the wafer, these will be evaporated, and at the lower side they will remain in the wafer, and these oxygen precipitates will create dislocations which will act as a Gettering center, as a sink, which will collect the metallic impurities. So you can use this oxygen which precipitates, and which is also present in the crystal. That is why it is known as intrinsic Gettering. So next is the float zone process. This is another method which is used to form the silicon, single crystalline silicon. In this method, we have this silicon bar, we have this silicon rod which is pure, and at one end we have a silicon seed. Suppose we have a silicon seed here, and we have this RF heater, and this RF heater, we can move that RF heater in upward and in downward direction. And with the help of this heating process, that when this rod comes in contact with the silicon seed, that will be melted, and that properties of silicon seed will be transferred to the silicon rod. So in this method, in float zone process, it has some advantages of CZ over the CZ method. For the growth of certain types of silicon crystal, the molten silicon in the float zone apparatus is not contained in the crucible. We have only RF heater which we can rotate from upside and downside, and thus it is not subjected to have any oxygen contamination, right? So in in float zone process, it is necessary to obtain the crystal with a very high resistivity, that is greater than 25 watt per centimeter. Next is wafer shaping. After the growing single crystal, it is first grinded to get a perfect cylinder with a precise controlled diameter. That diameter is precisely controlled with the help of process parameters which are present in CZ furnace. And most silicon ingot are grown along the direction, and the silicon cylinder is cut into individual wafer with a thickness of 775 micrometer thick, and that is done by using the diamond tipped inner hole blade saw or wire saw. Wafer shaping involves a series of precise mechanical and chemical process steps that are necessary to turn the ingot into the sectional wafers, and this method is called multi-wiring slicing, that is MWS, and it is a dominant state of art of slicing technology. In case of MWS, a thin wire is arranged over the cylinder and then it is cut into number of wafers. So this is the grinding diagram where we have the silicon ingot and we have a diamond cup wheel which is used to cut the silicon ingot into the slices. So after this grinding, we have to fix the diameter. One or more flats are grounded along the length of the ingot. These flats, the larger flat is known as the primary flat and the smaller one is known as the secondary flat. These flats are indicated so that the designers or the fabrication engineers can identify the which type of wafer or which orientation of wafer they are using. So, so the largest flat is called the major or the primary flat and is usually used to specify the crystal orientation. This primary flat is used to specify the crystal orientation, and this flat is located by X-ray diffraction technique. The primary flat serves as a mechanical locator in the automated processing equipment to position the wafer and also serve to orient the IC devices relatively to the crystal. And we have another flat, that is the secondary flat, which is used to identify the orientation and the conductivity of the wafer. So in this diagram we can see that if your primary flat is on the right side and at the 45 degree we have the secondary flat, we have 111 orientation and it is of N type. And if we don't have any secondary flat, we have a P type wafer with the 111 orientation. And secondly, if we have 100 orientation, then your primary flat and secondary flat are on the opposite side at 180 degree. And in case of N type, and in case of P type, we have primary flat and secondary flat at 90 degree. So one simple drawback of these flat is the reduction of usable area of the wafer. The slicing determines 4 wafer parameters. First one is the surface orientation, that what would be the surface orientation, whether we are using 111 orientation or 100 orientation. What would be the thickness of the wafer, that is 0.7 to 0.5 mm depending upon the wafer diameter. Taper, which is the wafer thickness variation from one end to another end, and how these wafers are sliced. Next, the wafer, when we cut it, when the silicon ingot is cut into the wafers, next step is the lapping. It is the operation that is performed under the pressure using the mixture of aluminum oxide and glycerin. It is used to remove the chemical. It is another process which is called chemical etching, which is used to remove the remaining damages which are contained in the region. And polishing is the last step. It is used for the purpose of so that we can have a very smooth specular surface on which your device can be photo engraved. This is the diagram which shows the polishing pad. Some slurry material is used so that wafer can be polished. This is the wafer holder, and some pressure is maintained so that this wafer can be maintained throughout the process. After this lapping process, wet etching process is used, which is used to remove the damages which may occur because of the process. Thus, wet etching, it can be used to remove 10 micrometer from both sides of the wafer. The wet etchants, the mixture of nitric acid HNO3, hydrofluoric acid HF, and the acetic acid CH3COOH can be used as the solutions for the wet etching. They will react with the silicon and may form the silicon dioxide, and the usual formulation is 4:1:3 mixture of nitric acid with 79% weight in water and hydrofluoric acid with 49% weight in water, and your acetic acid is used as a pure. The chemical reaction which is used in wet etching process is expressed as this silicon plus nitric acid plus hydrofluoric acid. It will give you this H2SiF6 plus water plus NO, nitrogen oxide. After this chemical etching, the next process is the lapping process, which is known as wafer polishing process. It is a mechanical chemical polishing technique. It is also known as CMP. The wafer is held on a rotating holder and pressed on a rotating polishing pad with the slurry and water in between. It is the same diagram which it is shown here, where some polishing pad is used, wafer holder is used to hold the wafer, and some pressure is maintained so that your wafer can be fixed. The slurry is a colloidal suspension of the fine silica SiO2 particles with a diameter of about 100 Armstrong in an aqueous solution of sodium hydroxide. Sodium hydroxide oxides, which is a chemical which in a chemical process the silicon surface with the help of heat generated by the friction between the wafer and polishing pad. These the post CMP process is a cleaning process with a mixture of acid oxidizer solution. It is used to remove the organic and inorganic contamination. Both type of contamination can be removed, and there are two processes which can be used. One is RCA1 cleaning technique and the another one is RCA2 cleaning techniques. And although same cleaning solution, that is HNO3 and HF and acetic acid, those chemicals are used in RCA clean 1 and RCA clean 2 process. And then the wafer which we get from after this polishing technique is free from the defects and is ready for the IC fabrication. So this is the another diagram which we can which is used for this chemical mechanical processing polishing technique. We have this pad. Here your wafer is placed, some slurry material is passed. This is the pad container, and some downward force is required so that your wafer can be held tightly. So at the back of the wafer, your defect and dislocations are intentionally created to trap the heavy metal, mobile or oxygen, carbon or another alkaline contamination. As mentioned in the earlier section, because these contaminations may lead to the device breakdown. It will lower down the breakdown voltage, and finally it will lead to the device breakdown. So we have to collect these metallic impurities throughout the process. So sometimes intentionally dislocations are created, and sometimes with the help of those oxygens which are already present during the growth, we take them as an advantage so that all these impurities can be collected and they don't disturb the device fabrication process. And backside defect can also be created using the argon ion implantation, polysilicon deposition and heavily doped phosphorus. And during the fabrication, the backside of the wafer is usually always deposited with a chemical vapor deposition, CVD, silicon dioxide or silicon nitride Si3N4 layer to prevent any out of diffusion during the thermal process. So this is the final wafer which we are going to use to fabricate any IC. Not this complete wafer is used to fabricate one device. This wafer is finally sliced into rectangles and they are cut into smaller sizes, and on each square one IC can be fabricated. Okay, so so this is all about first unit. That in the first unit we have covered that what basically is silicon, how this silicon crystal is used, how the silicon crystal is used as a to design this wafer, how the silicon ingot is grown. We initially grown this silicon ingot with the help of the Krolsky method, and that silicon ingot is cut into shapes, right? Is cut into shapes, and then these wafers are polished their defects are studied, that how many defects are present in these wafers, how many defects can be present in these ingots, and how these defects can be monitored, how these defects can be used in our advantage, and how these wafers are sliced to have the, which can be used as a foundation for any IC technology. Thank you so much.